Hello, good morning everyone. My name is MD Jamil Sam Khan. My presentation is about closing the loop in steel rolling and roll forming. In simple terms, the idea is to use the machine's own response during forming, especially load and torque signals, as the evidence of whether defects are likely to occur. The topic matters because advanced high-strength steels are available in lightweight engineering, but they are also harder to form accurately. I will briefly explain why the problem matters, what literature shows, the research gap, and caution and the research design proposed in my final report. The aim is to keep the explanation clear for a general audience, not only for manufacturing specialists. This slide shows the practical problem. Roll forming gradually bends a steel strip through a series of rollers. Advanced high-strength steel gives a strong and lightweight parts, but it is less forgiving during forming. Several defects can appear, like bow means the product is not straight along its length. Spring back means the part relaxes after the load is removed. Thinning weakens the section and the local fracture can make the part fail. This creates a quality control challenge. The research therefore focuses on measurable load signatures and forming parameter optimization so that quality problems can be predicted and reduced earlier. The literature points three connected themes. First, material behavior matters because strength, hardening, anisotropy, microstructure influence how steel bends, recover, and fails. Second, process parameters such as forming angle, reduction, speed, and roll geometry strongly affect strain distribution and dimensional accuracy. Third, modeling and optimization methods can predict defects and guide better control, especially when calibrated using the real data. The key synthesis is that these themes should not be treated separately. A strong design needs to connect material behavior, process control, and predictive modeling in one integrated workflow. The research gap is the missing closed loop. Theory studies often examine material behavior, forming parameters, defects, or modeling separately. The proposed question asks how measurable process load signatures and forming parameter optimization can be combined to predict and reduce bow, springback, thinning, and fracture risks. The closed loop idea is important as process settings create a machine response, sensors capture load and torque, a model maps those signals to defect risks, and the result can guide safer settings. This turns a trial and error process into a more data-driven quality control process. The proposed design combines laboratory evidence with simulation and data analysis. On the experiment side, advanced high-strength steel is formed through a controlled roll forming line. Sensors record load and torque in real time, and the final profile is checked for dimensions and defects. On the modeling side, finite element simulation helps estimate stress, strain, thickness, and spring back. The experiment and simulation are compared through accuracy checks and repeated trials support repeatability. This design is suitable because it links physical observation with prediction and optimization rather than relying on a single method. This slide explains the variables and measurement in general audience terms. The study changes controllable inputs such as forming angle, station spacing, bend angle, line speed, and sheet thickness. During forming, load and torque sensing record what machine feels, while geometry scanning records what happens to final profile. The measured responses are bow, spring back, thinning, and fracture tendency. The value of the data flow approach is that all measurements are time stamped and linked to input settings, so the final part quality can be explained rather than guessed. A good research design should explain both its strengths and its limits. The main strength of the design is alignment, the variables, measurements, and outputs, all the answer research question directly. It also combines laboratory testing, simulation, and validation, so the conclusion would not rely on modeling or only a single experiment. The limitations are also important. The design is still a mini-thesis design, so it is restricted to a selected material, thickness, profile geometry, and laboratory settings. It does not yet prove full industrial scalability. However, those limits are acceptable because the purpose is to create a defensible and measurable framework that can later be expanded to more steels, profiles, and factory conditions. The expected contribution is a practical framework for intelligent rule forming. The process starts by sensing the manufacturing line, then predicting defects and quality outcomes, then optimizing process settings, and finally validating whether the improvements are real. This moves the process from trial and error to a data-driven defect control. The broader benefit is lower scrap, better part quality, faster optimization, and stronger competitiveness for advanced high-strength steel products. My final message is that better measurement plus better predictive models can make high-strength steel forming more reliable. These are the main sources used in the presentation. They support literature synthesis across roll forming defects, springback, fracture, material behavior, rolling control, and optimization. In the presentation itself, I would not read the full reference list. I would use the slide to show that the work is evidence-based and that design has been built from a range of journal articles and technical sources. Thank you. Thank you for receiving me.